Hello everyone, thank you very much for watching this talk. My name is Gordon Brown. I'm a principal software engineer at Codeplay, where I'm the technical lead on the ComputeCpp runtime, as well as a contributor to the SYCL working group in Khronos. In this talk I'm going to be giving a sneak preview of SYCL 2020. This is the most recent revision of SYCL. I'll be diving into some of the new features that we expect to be included and demonstrating how you'd use these in your SYCL applications. Unfortunately, this isn't a live talk, so I can't answer questions directly, but I will provide my details at the end, so you can get in touch with me if you have any questions. So I'm going to start off with a brief history of SYCL so far. SYCL first emerged back in 2015 when the SYCL 1.2 spec was ratified. The first implementations were Codeplay's ComputeCpp and an open source project called triSYCL, which is led by Reyes, who's now at Xilinx and is the spec editor for SYCL. Over the next 2 years, we gathered a lot of feedback from users about what features they liked and what features they'd like to see, and based on this, we shipped a major update called SYCL 1.2.1. The following year, ComputeCpp became the first conformant implementation, and what this meant is that it fully implemented the spec and passed the conformance tests that are set by Khronos. Then over the following couple of years, 2 new implementations were introduced. Firstly, there was hipSYCL, which is an open source implementation led by Axel Alpe at Heidelberg University. And this runs on top of hip for AMD and NVIDIA GPUs. Secondly, there was Data Parallel C++, which is another open source implementation led by Intel, forming part of their oneAPI solution. And over the years, there have been many extensions from the various different implementers proposing new features to SYCL. And more recently, Data Parallel C++ has been extended to support running on top of CUDA in addition to OpenCL. And this brings us to today, where I'm pleased to be able to share with you a preview of the latest revision of SYCL that is currently in the works. However, before I do, it's important to note that everything that I'm going to be presenting here is still a work in progress. And while the SYCL group are very confident in these features, they are still subject to change, so you should take this as an indication only of what to expect. So the next revision of SYCL is going to be SYCL 2020. As you can see from the name, we've decided to move to a new naming convention which follows the year the revision is released rather than a specific version of OpenCL. And this will make more sense when we dive into some of the features. Now here we have a list of some of the core features that we expect to be included in SYCL 2020. Now, unfortunately, I don't have time to cover all of these features, and many of these will actually be covered by some of the other talks at IWOCL this year, so I definitely recommend you check those out. I'll be focusing for my talk on 3 of these features, those being backend generalization, modules, and then host tasks. So first up is backend generalization. So SYCL 1.2.1 is based on OpenCL 1.2, which means it supports any OpenCL 1.2 device. Now SYCL 2020 is going to go further than this to support additional backends as well. Now the execution and memory models will remain the same, and the API will be largely unaffected by this change. But what this means is that SYCL runtime will now be able to support devices from additional backends as well as those from OpenCL 1.2. Now, OpenCL 1.2 will remain a core backend for SYCL, but implementations will now also be able to support later versions of OpenCL as well as other non-OpenCL backends such as Vulkan or CUDA. So here we're taking a look at how these changes will affect the SYCL ecosystem. So much of the SYCL ecosystem stack will remain the same. We still have SYCL applications targeting the SYCL API, and those applications are still running on a SYCL runtime. However, before in SYCL 1.2.1, where we had a host device and an OpenCL device, we now have a number of backends, including a host backend. Now it's important to note that this is not representative of current SYCL implementations. This is just an indicator of what you could have in SYCL 2020. So there are a couple of important things to note here. Firstly is every SYCL 2020 implementation must have a host backend. And secondly, every SYCL 2020 implementation must have at least one device backend. Now we're going to take a look at how the SYCL topology structure has changed to support these new backends. So you're probably familiar with the SYCL topology of SYCL 1.2.1, where we have platforms and devices. But now in SYCL 2020, there will be a further layer for representing backends. Now here in this example, we have a number of devices and their platforms, and these are grouped together into different backends. In this case, they're OpenCL, CUDA, and then host backend. Again, there are a couple of important things to note here. Firstly, the host device and platform always exist in the host backend. Secondly, it's important to note that in a SYCL 2020 implementation with more than one backend, it's possible for the same physical device to be represented by two backends. This is the case in this example here, where we have an NVIDIA GPU that is represented by both the OpenCL backend and the CUDA backend. So this is something to be careful of when you're selecting devices for your applications in order to avoid contention for the same device via different backends. So one of the other changes that comes with the backend generalization is a clarification of the customizability and portability of SYCL applications. The way this works is that SYCL applications can be divided into three categories. There's generic SYCL, interoperability, and backend specific. So firstly, looking at generic SYCL, this includes anything developed against the standard SYCL programming model. These applications will be fully portable across any SYCL implementation. This means that an application written against one SYCL implementation will be portable to any other implementation. Next, we have interoperability. So if for any reason an application needs to interoperate with the underlying API of a backend, you can do this using the SYCL interop API. Now this API is standard, however, as it uses the native objects of the specific backend that you're targeting, it's only portable to other implementations which also support that backend. So for example, if you wanted to interoperate with the CUDA API, then that application would only be portable with other implementations which also support the CUDA backend. Finally, we have backend or vendor specific. So in the extreme case, when you have an application where you want to take advantage of a specific extension that's only available to a very specific backend or vendor, you can do that. However, that application would then only be portable to an implementation which also supports that extension, which in some cases is only that implementation, which means it wouldn't be portable at all. So here we have an example of using backend interoperability with SYCL 2020. So here we have an algorithm which takes a queue and an input buffer and an output buffer, and it's going to do some kind of computation with a number of kernels. And we want to specialize this for the OpenCL backend. Now, an example of why you might want to do this is, say you have an existing OpenCL C kernels in some other library and you want to interoperate these with the SYCL runtime. So the important thing to note when doing this is that anytime you interact with a backend, so any function which is specialized on the backend becomes non-generic SYCL, which means that it's not necessarily portable with other SYCL implementations. So we recommend that you always guard this code with the macros for that specific backend. We also recommend that you have a fallback to a generic implementation in the case that that backend doesn't exist, in order to try and maintain as much portability as possible. So one of the first things that you want to do when interoperating with a backend is to be able to take an existing SYCL object and retrieve the underlying native object for the backend that you're targeting. So you do this by calling the getNativeFree function. Now this function takes a template parameter that is the backend enum class that specifies the backend that you're wanting to interoperate with. In this case, it's backend OpenCL. And then the getNative function also takes a parameter for the SYCL object that you're wanting to retrieve the native object for. In this case, we're wanting to retrieve the native queue for our SYCL queue. And in some cases, you often have to pass the SYCL context that you're associating this as well to disambiguate between other contexts. And what's returned from this function is the native object that is associated with the object that you pass in. So here we now have a OpenCL command queue. And then once you have that native object, you can then pass that on to another library, which will be able to use that object to enqueue kernels. In this case, say that library function returns a OpenCL event that you can use to synchronize with that work. Now, once we have that, we'll want to then be able to resynchronize with the SYCL runtime to allow any future SYCL kernels to wait on that work to complete. Now, to create a SYCL object from a native object, there are other free functions. In this case, we're going to be using the makeEvent function, which again takes the backend OpenCL parameter to specify the backend you want to interoperate with, and it takes a native object, in this case a CL event, and again that's to take a context to be able to disambiguate which context you're wishing to create the SYCL object for. So now here we've created a new SYCL event based on that native OpenCL event, and from there we can call wait on that event just like you would any other event. And what this will do is it will wait for the work that you've enqueued through interop to complete before it continues any other work. So the next feature I'm going to discuss is modules. Now, modules in SYCL 2020 are a replacement for the program class from SYCL 1.2.1 to add some additional features and improve on some things from 1.2.1. One thing that's important to note is that modules in SYCL 2020 are a different concept from modules in C++ 20. So the program class in SYCL 1.2.1 had a number of issues with it moving into SYCL 2020. So the API was very tightly coupled with OpenCL, and therefore it wasn't general enough to map to other non-OpenCL backends. The compile, link, and build member functions of the program class were found to not be able to be efficiently implemented to be thread safe. There was no representation for the file formats of a program. And finally, there is no association with the kernels defined in a particular translation unit. So based on these, it was decided that for SYCL 2020 we would redesign how this works to try and improve on some of these things. And the result of this redesign was modules. So what is a SYCL module? So a module is an object that represents all of the kernels that are defined in a particular translation unit. So for example, if you have a translation unit that defines two SYCL kernels, one named foo and one named fizz, then if you retrieve the module for that translation unit, then that module will contain both of those kernels. And a module can contain one or more what we call device images. A device image is a file format that represents the binary representation of those kernels. Now this can be in a standard intermediate representation such as SPEAR, SPEAR-V, or it could be some proprietary representation such as GCN or PTX. It can even be a compiled instruction set for a specific architecture. Now one important thing to note here is that every device image within a module must contain all of the kernels and other symbols required to represent all of the kernels of that module. Now, a module can be in one of three different states, and that state is part of the module's type. So there are three different states: are input module, which is some form of input source, which can be either like something like OpenCL C source, or it could be an intermediate representation such as SPEAR-V or some other proprietary IR. They then have an object module, which is a compiled binary in any file format, which can be linked with other object modules to form an executable module. An executable module, as described, is a fully compiled and linked binary in any file format. An executable module are the modules that can be executed with a SYCL kernel function. Now, there are a couple of different ways that you can build your modules. Now, from an input module, you can compile it, and that will result in an object module. Then from the object module, you can then link it into an executable module. However, you can also build an input module, and that will combine both the compilation and linkage and result in an executable module. So there are a few important things to note about modules in SYCL 2020. So firstly, kernel invocation APIs such as Parallel4 will continue to work as they did before. If you provide a kernel object to these functions, the runtime will use the kernel and the module that's associated with that when it executes the kernel. However, if you don't, then the runtime will implicitly compile a module for you and use that. A module state is part of the module class type, And the compile, link, and build operations are now free functions which each return a module of the resulting state. So this is all now type safe and thread safe. There is a module associated with each translation unit, and this can be retrieved by calling this module get. And finally, there's now more control over which device image you choose when you execute a kernel. So you can specify the module that you wish to use for a particular command group by using the use module member function of the handler. But when you do this, you can also provide what's called a device image selector, which allows you to manually choose the device image that you wish to use to execute the kernel in the case that there's more than one available. So here's an example of how you would use modules in SYCL 2020 to manually compile the kernel that you wish to execute. So the first thing that you have to do is you need to retrieve the module that's associated with the translation unit. So you do this by calling this module get. Now this function takes a template parameter for specifying the module state. And in this case we're requesting an input module. And then you also have to provide a context for which you want to retrieve the module for. Now you can retrieve a module in the object or executable states as well, and in this case the runtime will implicitly perform any compilation or linking steps that are required in order to retrieve that module if possible. Now that we have our input module, we need to build this in order to obtain an executable module. Now to do this we simply call build and then pass in the input module, and then this will perform the compilation and linking steps required and then return a new module of executable state. Now these functions such as build, link, and compile also accept an optional properties list which allow you to specify specific flags or compilation or linking options to customize how your module is built. Next, we need to retrieve a kernel object for the particular kernel that we're executing. In this case, is kernel foo. However, there's a get kernel function on the executable modules only that takes the string name of a kernel and returns a kernel object. So first we need to retrieve the string name of a kernel. In this case, we use a variable template on this module namespace called kernel name, where you specify the template parameter, in this case foo, and you get back the string version of that name. And then we pass that into get kernel in order to retrieve the kernel object that we want. Finally, in order to use this module and this kernel when we're executing the parallel for, we need to do two things. First, we need to call use module on the command group handler, specifying the executable module. Here we can optionally also pass a device image selector if we wanted to choose between different device images. And then the next thing we have to do is, as we did before in SYCL 1.2.1, pass the kernel object to parallel for to specify the specific kernel object that we want to use. So lastly, I'm going to cover host tasks. So it was found that SYCL 1.2.1 was missing some useful scheduling features, such as there's no way to asynchronously schedule arbitrary C++ code to do callbacks, and there's no way to asynchronously interoperate with SYCL memory objects and SYCL queues within the SYCL DAG. So it was decided for SYCL 2020 that we would introduce host tasks. And host tasks in some form have been available as an extension in ComputeCpp for quite a while now. However, there's been a redesign of the feature for SYCL 2020 that now includes interoperability as part of it. So here's an example of how you'd use host tasks in SYCL 2020. So the host task function is a member function of the handler, same as some of the other APIs at parallel for and single task. However, host task schedules arbitrary C++ code running, although following the same rules as SYCL kernels. So the function that you pass into host tasks isn't bound by the same rules that SYCL kernel functions are. They can do anything a regular C++ application could do. And just as with regular SYCL kernels, data dependencies are defined using accessors. So here we're using host buffer accessors And when you use host buffer accessors, you are requesting access to the data managed by those buffers on the host to be made available to the host task. So this means those accessors are directly accessible in the host task, so you can read and write to them directly. So here's another example of how you'd use a host task in order to do interoperability. So you can do this with quite a simple change. You just add the extra optional parameter to the host task, a lambda or function object, that is the interop handle object. And this object is used to provide all the interoperability functionality. As with the previous example, accessors are used here to create data dependencies for the host task when you're doing interoperability as well. However, when you're doing interoperability, you want to use global buffer accessors rather than host buffer accessors. And what this does is make the data managed by those buffers available on the device associated with the queue submitting your host task. Now this means that those accessors are not directly accessible in the host task, as with the host buffer accessors, but they can be used to retrieve the underlying native objects. Now, in order to retrieve the native objects of an accessor or of the queue that submitted the host task, you can call the getNative member functions of the interop handle. And these member functions take a template parameter, which specifies the backend that you're targeting. In this case, this is backend OpenCL. And in some cases, they also take SYCL objects that you wish to retrieve the native objects for. So first we call getNative queue. Now this doesn't take any parameter and it returns the native OpenCL command queue of the SYCL queue that you submitted the host task to. Then we call getNative mem for each of the two accessors, passing in the accessor and then returning the native OpenCL mem objects associated with those accessors. Now once we have those native objects, we can now queue work directly to them, and this will all be called at the point where the host task is invoked. So to conclude, SYCL 2020 will be a significant improvement on the SYCL standard with a number of great new features that we hope will improve SYCL application development and grow the ecosystem. The SYCL working group are aiming to ratify a provisional specification of SYCL 2020 summer this year, and we look forward to people's feedback on that when it comes. Thank you very much for watching this talk. This is my email address here, so feel free to get in touch with me if you have any questions.